So my name is Evan. I'm a principal engineer at Conviva, and I'm really excited to be and thankful to be invited back here to speak at Scale by the Bay. It's really nice to have in-person conferences again. So good morning, everyone, and let's get started. So a little bit of a word about my employer. Conviva, what we do is that we do streaming real-time user experience analytics. What does this mean? So a lot of our customers are like some of the biggest streaming companies out there. Like you could be like HBO, Disney Plus, and basically what we tell our clients are like what trouble people have when they in this case, it's watch video, but you can imagine like surfing the web. It's basically to tell them like what is happening with users all over the world. And we have massive real-time streaming analytics pipelines. It does 5 trillion events processed per day. A lot of people talk about billions as being a lot, but we're at a couple orders of magnitude beyond that. So this is like a really massive pipeline. And we started with some custom Java code and went through a couple iterations. And today we have hundreds of pods serving some custom Akka streaming stuff. So it's pretty cool, large-scale work. But today I'm going to be talking to you about our experience porting stuff to Rust. And what we see is that the data world is going native. Why is that? Well, we can probably thank Python and the rise of AI and ML to data science to some of this. It has become really big, and like even all the existing JVM ecosystems like Spark have had to adapt and be able to run like C Python workloads. We can probably thank the end of Moore's law for some of it, being that CPU speeds are not increasing. What we see is that we have an increasing number of GPU cores and things like that. So being able to take advantage of those is becoming really important. Maybe we can thank some cloud stuff. So why Rust in particular? Well, it is safe, fast, is in like C, C++ kind of fast, and it has good high-level abstractions, has support for functional data patterns, pattern matching, and so forth. And we see that there's a lot of projects that are starting to come out that are starting to like be really interesting, like that people are starting to use. And we can map those from the old JVM frameworks like Spark and Hive. Well, now we have things like Data Fusion. How many people have heard of Data Fusion? Like almost nobody. So, Data Fusion is a modern SQL executor, and Ballista is the distributed version. You can think of it as like a new Spark SQL. There's some other interesting projects on this list. There's a bunch of new streaming frameworks. Rising Wave, Arroyo, Materialize, they all do streaming SQL or streaming materialized views. And even in the traditional, like for Kafka, there's a bunch of new folks that are coming out. I didn't list here like Red Panda is in the new one. Fluvio is a Rust-based persistent queue that has stream processing. So there's a lot of new stuff that's coming out. And so it's a very, very exciting area. Even in terms of databases, there's Rust-based database projects that are coming out, even in terms of graph. TerminalDB is a really neat one that not only does graph, but does versioning as well. So there's a huge amount of momentum. And I think there's some other Rust talks that I saw on the schedule, and maybe if I went last instead of first, would list some of those on my talk. So a little bit about our architecture. What we have is that we have a bunch of sensors that gather data and send it to a massive array of gateways on our backend. This goes to, this is massively simplified, of course, but this goes into Kafka, then it goes into a big streaming data pipeline, and then the pipeline computes metrics, which goes into database and gets served to users. So nothing really like, at least at this picture level, it doesn't look that complicated. So what we are porting to Rust first is this big box, a stream pipeline. We wanted to take that and both increase the efficiency because at our scale, at trillions of events a day, this becomes pretty important. And second, we wanted to upgrade the pipeline to be more flexible so that it could be more dynamically programmable. And we'll talk about that in a little bit. Second, we were having some issues with our gateways. We wanted to increase that, make that more efficient, and fix a few things. So that got upgraded a couple times. And lastly, there's some work with sensors. You have a lot of different small code bases because you could have something that's written in Swift for iOS, something that's written in Android, Java, and C, C++, a lot of different types of frameworks. So it's kind of nice to be able to try to unify some of that if possible. So this is what our journey looks like to Rust. So for the data pipeline, we started out with a hackathon about a year ago. And this is just to see, hey, let's try this new thing out. Let's see what the ecosystem is like. What is it like to develop in it? What are some libraries? So, and then we proceeded to, we were porting a data pipeline to a new platform. Initially, a Scala prototype was written. Then we spent a month and a half doing a Rust port of the new Scala pipeline. After a few months, we got more comfortable and brought on a lot more people. And that's this bigger bar, that says, bring on more people. And that's kind of our current phase. We're bringing on a lot of new people. Now they've gotten used to it. And now we have up to 20, 25 people across a couple teams working on this new code base, which is pretty exciting. There was also an effort to port the gateway, and the gateway was ported from a JVM code base into Go first, and then it was ported from Go to Rust because we saw some benefits there. So that's pretty interesting. So a little bit about this Rust hackathon. Basically, what we did was we took a really simple part of the data pipeline that just reads data from Kafka, deserializes, and does some really lightweight processing. So this was really an IO-bound workload. It was just to get a feel for, hey, what is it like to work with? What is it like to work with async Rust code? What is it like to work with some really basic data processing? Oh, sorry, I realized I'm speaking to the mic. And we were able to get some good gains out of that, kind of like 2.5 times more CPU. The memory increase was more impressive. That was like 12 times less. And so that was promising enough to try new things. Although at that time it wasn't clear if it was worth the effort, like how much effort or time we would be able to put into it, or like if it was, but it was the performance results were impressive, right? And we also learned some things about active frameworks in Rust. We also have some results from porting the gateway. This is pretty interesting. The graphs here compare not JVM but Golang. So the team initially ported JVM code to Go, which seems like a pretty good choice. It's high productivity, and it was pretty interesting. They also found that even compared to Go, like Rust was able to halve the CPU consumption and also decrease the memory use by an order of magnitude. So that's a really interesting finding. So when we do a port, we want to ask ourselves some key questions. I call these the 4 Ps. So you can like tag along with me here for a sec. One is people, like how do we bring people on board? Another one is performance. A third one is what I call patterns. It's like how do you adopt existing, what coding patterns you're used to into a new world. And the fourth one is projects, which is more about tooling, debugging, and so forth. Although yeah. So let's dive right in. So people, how do we bring developers on board? And in the end, this is like one of the most key questions, right? It's that if we can't bring the people on board, then it's like really, really difficult. So what we did was that we did a phased bring up. So the initial phase was that we had a very small team of 3 to 5 very senior folks with at least 1 or 2 people that was more experienced in Rust. I guess that person was me. And we did the core part of the port. We ported a big majority of the code. And we had a second phase a few months later where we brought in a lot more folks, the 10 to 15 folks that have mixed levels of experience from more junior to more senior folks. And pretty much none of them had Rust experience. And what we did there was that because we did this in a second phase, we're able to give them more time, to come up to speed, to kind of like, I think on average, probably took 2 to 3 weeks. We just gave them some time just to learn, just to read. But at the same time, the benefit is that we had a team that already came up to speed, and so we were there to help, answer questions and help along, and to basically guide them to do, hey, like start here and this kind of thing. And you can see it. There's a lot of challenges when you learn a new language, lifetimes, compiler errors, how to do this or that. We'll get into some of this later. Ownership is a big question, and I think the tools that we found very helpful. I think some of it has to do with good project organization. We split the project into a streaming asynchronous part and synchronous part, and so it's a little bit easier on ramp. Some folks didn't have to learn certain parts, and having good documentation and other things like that is always really helpful. But specifically to Rust, there's a really helpful Rust book. A lot of people found ChatGPT actually really useful just to help them get started. It's not always the most accurate. Might give you like kind of wrong answers-ish, but it's kind of like helps you get over hump or get started. And another thing that we found helpful that started doing a couple weeks ago was to have office hours. This is just like say 1 hour a week kind of thing, just to offer folks, hey, this is a time when you can ask questions, and found a lot of folks coming by to just to chat about what difficult things they're having. And I think it's you can't really replace spending a lot of time on things like reviews, just to help people with like a lot of detailed things. And now we come to one of my favorite topics, performance, talk about data structures and so forth. One of the quotes from one of our engineers was that they enjoyed the fact that the default routes in Rust is for performance, and that if you want to choose a path that is less performant, usually you need to type in like extra keyword, like box or something. Okay, so take these numbers with a grain of salt, but basically I'm going to be talking a bit about porting our main data pipeline, and neither of these, I say take a grain of salt because neither of these have been like heavily productionized or anything like that. They were at the time they reported was more early stage, but it's the same architecture, the same inputs and outputs. The Scala version wasn't designed for speed. In Rust, when we ported it, because in Rust, one thing is that you have to spend a lot of time thinking about data structures. So when we ported it, we purposely chose to use some streamlined data structures to minimize allocations. So we got a pretty big boost comparing the two, like a little more than order of magnitude. And so it's been very promising so far. So what this data pipeline does is like a whole bunch of stream and complex event processing, which is very stateful. And the goal of our new pipeline is that we want to be able to let people program a directed graph of data operators. So you can imagine that data comes in on the left side, and we extract some data out. We do some transforms. We bring it back together. So forth. So you should be able to rearrange these, and these data operators connect time-ordered data, and we call a breakup of the times spans. And so basically, an executor connects data from operator to operator, kind of like an Airflow DAG, but on a much smaller scale. So this is more like maybe like a database query compiler, so forth. So, and the data is broken up into multiple spans where each span would have a time range and some data. Now, if I was to, so I'm going to spend a little bit of time on this diagram. What the left and right sides represent are the different ways that data structures look in Scala or the JVM versus Rust. So in Scala, we start out with something we call a timeline, which is a bunch of spans or a bunch of data organized by time. And this is typically something like a seek or buffered iterator or something like that. And underneath, you would have arrays, right? So the seek is typically a separate object. In the JVM, the array is its own object, so the seek points to the array, right? And then the array itself, because the spans underneath, it's an array of spans, underneath they are not primitives, so again, the array would point to more objects, each span is its own object, and if that span has a somewhat complex type underneath, like it has a set of events, that would be its own, again, so it's object. So again, you have like 3 or 4 or 5 layers of object wrapping. In the Rust side is the equivalent, but due to a couple techniques, we can, in most cases, we can actually have the entire data structure sitting in line on the stack. And that's why you see they are wrapped in boxes instead of arrows. And the way that this works is that one thing is that having structs helps you inline things. So because a struct is fields of a known size that are all inline, they can sit one after another, even in something like a collection, like a list. The other thing that we do is that we use data structure that I'll get into a little bit later that allows us to, for a small number of elements, to inline them on the stack. What this looks like is at the top level we have an enum, and then underneath we have something called a small vec that holds, a vec is a list. This holds a list of items, and then underneath that, the list of items are spans, which are structs, and they can have other things inside. And so basically, if the number of spans and the number of events are small, then they can all fit inside the stack. So I'll just go a little bit into, it's not really magic. This is something called a small vec. And the way this works is this is an enum, which is like a sum type. And it can be either, say, something that fits on a stack, or something that sits on a heap. So it's one of those two, and then the class manages that. So then basically the stack one is of a limited capacity, n here. It holds up to n items. And if you exceed that, then basically this thing becomes a heap variety. So it's pretty simple, but pretty effective way of avoiding allocations. And there's a whole bunch of other crates that are like that. So, but this is one of the really neat things you can do is that you can control your layout really precisely and in Rust. Another important topic is about static versus dynamic dispatch. In Rust, you can have very precise control over where you want or what kind of dispatch you want, but dynamic is not by default. So let's say that you want to work with different kinds of structs that implement some trait. And so this is a pretty common pattern. So there's a couple different approaches to the dispatch. The fastest and maybe the easiest is this big word called monomorphization, which is basically that in your function signature, you have this trait. In this case, we have this O, this type O, which something that implements operator. And the compiler will basically, whatever you pass at compile time, the compiler will make a version of this function execute op for that specific type that you put in, right? So this works well when you know the types in advance. Then a compiler can put out the can generate code for each different type that is needed, and it's direct and static and very, very fast, right? Sometimes that's not possible. In our case, because like the programmable DAG of operators is dynamic. So what we do a lot of times is that we use enums, because this is a sum type that has a type there at runtime. And I will go into that a little bit. So this is another technique. And for dynamic dispatch itself, if you want to go that route, there are even two variations. There's one that does not require boxing, which is neat for avoiding allocations, but it still requires a vtable lookup. And finally, you can do function wrapping. So a little bit about enum dispatch. What this is this is a macro where, in this case, we have two structs, the linear knob and the logarithmic knob, right? And they both implement this trait called knob control. And what enum dispatch lets you do is that I can have an enum called knob, which has the variance, and enum dispatch will generate trait implementations, and so that at runtime it can, depending on which enum variant it is, it can pass it to it's the inner types that already implement that stuff. And this is still significantly faster than doing a dynamic dispatch vtable lookup. One reason is because, especially if the code is small, the compiler can actually inline all the different variants, and so you're only paying the cost of the branch lookup instead of a dynamic jump instruction. Another technique you can do is this function wrapping. And so what this is that you can just have this function in line in your structs. There's two variants in Rust. There's a lowercase fn, which is a type, and there's an uppercase fn, which is a trait. So those two are different depending on your needs. The uppercase one is can be like closures and things like that. The lowercase fn is a constant. It basically is a pure function. You can't have you can't close over anything. I want to talk about patterns a little bit. So there's different paradigms. The predominant async paradigm in Rust is that there's an async await. There's a native async await paradigm that is often used. This is basically just asynchronous function calls, where basically you can define a function and you say, this is an async function, and Rust basically turns it into a future and does the magic underneath. There's also futures, but it's a lot more ergonomic to just use async functions. And finally, there's other things like actors and async streams and reactive as well, although none of these libraries are quite as well developed as in the Scala JVM world. We went through some iterations in trying out different actor libraries and so forth. We found out one of the dominant ones doesn't play well with the dominant async library in Rust, which is called Tokyo. And so we ended up writing our own little library, which sits on top of Tokyo because Tokyo has asynchronous tasks and so forth. So this is a really lightweight layer that sits on top and gives you an actor abstraction with the ability to send a message and and do an ask and so on. There's a bunch of other interesting patterns, which I think the most interesting is that there are no exceptions in Rust. You use the functional result pattern, and let's see, and there's no inheritance, so you just have to use composition, which is personally fine for me. So there's a couple of things to learn. I'm gonna quickly go into the project and stuff for a quick sec. One of the quotes from one of our engineers was that our cargo was the best build tool ever. I do find it like really easy to use because you just write Tomo, and I pretty much never have to worry about actual build code in terms of like say Rust code in order to build more Rust code, which is personally is really nice. I think that's one of the best things about the Rust ecosystem because like I don't really want to be worried about having to write code when I need something to build. So yeah, it works really, really well. And there's a bunch of tooling and other things like that. One thing I would give a shout out to is that VS Code has a really nice, it's called Live Share. It's like a pair programming tool that you can do, like especially for remote pair programming. Each person gets a cursor, and like it works really, really well. And there's a bunch of other, there's equivalent tooling for almost everything, property testing and so forth. There's a bunch of links, which I will share in the slides later, that you can see if you want resources for looking up projects and that kind of stuff. And finally, like I will say like a little bit, what do we miss from Scala? I think there's a few libraries that are a little bit more mature, like HDFS support, there's a few like obvious things like that. And I think finally, like for takeaways, it's been a long journey, but I think that it was quite worth it for us. It has very promising performance profile as well as safety. And I think that structuring your project and structuring how the project is run can go a long ways towards folks coming on board. And the other thing is to focus on data structure design early. And finally, we are hiring, so feel free to come talk to me. Thank you very much, and feel free to reach out to me on different platforms.